Hello, my name is Jacob Magdon, and today I'm going to be going over problem 2 on the exam, which was about a mass connected to a spring that was hanging at an angle. So I drew a picture of what this problem looked like, and first, the first question I wanted us to find out is the net force as a vector acting on the mass. So going over this one, something I like to do is just write out all the components that we need to know. So our net force is going to be equal to the spring force and gravitational force. And that's all we have acting on the ball. And gravitational force, pretty simple. Let's write that out as a vector is going to be 0, negative mg, 0, because it's pulling the ball down in the y direction. Now the spring force is a little bit more complicated, but pretty much it's just going to be what I'll write down is the spring force times the angle that it's at. And it may not be intuitive just by looking at it, but the x component is actually going to be our spring force sine theta, and the y component will be the spring force cosine theta. And this is because if you look at the picture above, we see that our angle is oriented in such a way that the sine of the angle is going to be this x component, and the cosine will be this up and down vertical y component. And so all we need to do now is use our equation for spring force, which is simply negative k L minus L naught, where L naught is the relaxed length and L is the stretched or compressed length that we have. Now we can just plug this back into our spring force and combine everything together for our net force. So as a vector, the only thing acting in the x direction is the spring force. So we're going to have negative k L minus L naught sine theta in the x component. Then the y is going to be negative k L minus L naught cosine theta minus mg, because we do have that gravitational force, and of course nothing in the y. So that is it for the first part. Pretty simple. And moving on to the next part, number 2. What this part is asking us is how far, or what's the change in the x direction the ball moves after it's released. And we are told that the change in the y is 0. And so what we can also get from this is that the net force in the y is equal to 0, which will be important. So just looking at the change in position in the x direction, we're going to write down delta x is equal to v average delta t. But in this case, the force is not constant because that spring force is going to vary depending on the length of the string. So we can go ahead and write down delta x equals vf delta t. So now we want to know what vf is. So our formula for final velocity is going to be initial velocity plus f net over m delta t. And keep in mind all of these values are in the x direction. Alright, so because it's in the x direction, our net force, I'll go ahead and write down in the x, is just negative k L minus L naught sine theta. And then we have the mass m, delta t. We don't know what delta t is, but we'll leave it as that. And then initial velocity is 0. So now we can just write out final velocity is equal to negative k over m L minus L naught sine theta delta t. All right, so now that we have final velocity, we can go ahead and plug this back into our equation up here and say that delta x is equal to negative k over m L minus L naught sine theta. And we have a delta t times a delta t on the outside. So we'll just hold this delta t squared out there. And here we are almost done with our problem. However, it does ask us to uh, write our answer only in terms of theta, gravity, and delta t. And so as you can see, we have like a spring constant, we have L's, L naught, and a mass. So we are not done yet. But luckily, so what I brought up earlier about the net force in the y direction being equal to 0, that's going to come in handy here. So if I write down under here, our net force in the y is 0, and we already know what the y component of force is, which we got right here. Let me use a different color. So we're going to use this right here. And since it's 0, we can set mg equal to negative k L minus L naught cosine theta. And then what we can do, we can notice that what we have here looks pretty similar to our equation for delta x. And if we actually divide both sides by m, we get that g is equal to negative k over m L minus L naught cosine theta. And as you can see, this is very similar to our delta x equation, except we have a sign in the delta x equation instead of a cosine, and we don't have that delta t. But that's okay because we are told that we can have delta t in our final answer. So to get rid of this cosine and have a sign instead, all we need to do is say g tan theta. And what that's going to do is that's going to multiply by a sine and divide by a cosine. So that cosine is going to cancel out. We'll be left with g tan theta is equal to negative k over m L minus L naught sine theta. And this is very good because we can see we can plug this in with this over here. And so now we can write down our delta x in the terms that we want and say g tan theta times delta t squared. And it looks much simpler, and we only have a few variables. And that is going to be our final answer. Thanks.